Look at the clock on your wall. The next moment is coming, and there is no direction you can turn to avoid it. Hold on to that feeling, because that, it turns out, is what waits at the center of a black hole. You have been told the singularity is a tiny point sitting at the dead center of the hole, like the pit inside a peach. It is not a point in space at all. Inside the horizon, something extraordinary happens to space and time. They trade places, and the singularity stops being a spot you could travel to. It becomes a moment you cannot avoid arriving at. This is the gravitational singularity, the place, or rather the moment, where our finest theory of gravity stops being able to describe the world. Fall into a black hole 30 times the mass of the Sun, and the strangeness turns personal. You would have less than a single heartbeat before you reach it, measured out about 2 10,000ths of 1 second. And fighting it, firing every engine you have, only makes that moment come sooner. In 1965, a young mathematician proved this was no accident of neat equations. His name was Roger Penrose. Let's step into his story. So let me answer the first question directly, before any history, before any names, because it is the question that made you click. If the singularity is not a point in space, then what is it? And why can no one point to it? Here is the mechanism at a first working level. A black hole is described, in its simplest form, by a piece of mathematics called the Schwarzschild geometry. It describes the shape of space and time around a mass, and that shape carries a strange feature. There is a radius, a specific distance from the center, where the character of space and time changes. Cross that radius and the roles of space and time swap. What was a direction you could move through freely in space becomes a direction that only runs one way, like time. And what was the forward march of time becomes a direction in space. Think about what swap means here concretely. Right now, you can move left or right, up or down, forward or back. 3 directions, and you are free in all of them. But there is one direction you cannot choose about at all, and that is time. You are carried into the next second whether you like it or not. You cannot steer sideways in time, you cannot stop, you cannot reverse. Now imagine that one of your spatial directions, the direction pointing inward toward the center of the black hole, became exactly like that. Not a direction you move through by choice, but a direction you are carried down, the way you are carried into tomorrow. That is the signature flip, and once you understand it, the whole picture rearranges itself. The center of the black hole, the place labeled r equals 0, is no longer a location in front of you. It is a moment ahead of you in time. You can no more point to it than you can point to next Tuesday. You cannot avoid it by steering, for the same reason you cannot avoid next Tuesday by walking north. What does it mean that down has become later? It means that inside a black hole, space becomes something you are pulled through helplessly, and the singularity becomes your future, not your surroundings. Let me put the mathematics on the table, because this audience deserves to see the actual object, not a cartoon of it. The Schwarzschild metric, written in 1916, reads ds squared equals minus 1 minus 2 gm over rc squared times c squared dt squared plus dr squared divided by 1 minus 2 gm over rc squared plus r squared d omega squared. Do not be intimidated by the symbols. Every one of them means something plain. The letter r is the radius, how far you are from the center. M is the mass of the black hole. The letter T is time as measured far away. And d omega squared just bookkeeps the two angles that tell you which way you are facing on a sphere. The whole story lives in one factor, 1 minus 2 gm over rc squared. Watch what happens to it. When r is large, when you are far away, that factor sits close to 1, positive and ordinary, and space and time behave exactly as your intuition expects. But there is a special radius where the factor hits 0. It is called the Schwarzschild radius, and it is r minus s equals 2 gm over c squared. For the Sun, that radius is about 2.95 kilometers, under 2 miles. For the Earth, it is about 9 millimeters, smaller than a marble. Compress a thing inside its own Schwarzschild radius, and it becomes a black hole. Now watch the sign. When r drops below the Schwarzschild radius, once you are inside, that factor turns negative. And a negative factor multiplying the time term and dividing the radial term does something violent to their meaning. The term attached to time changes sign, and so does the term attached to radius. Mathematically, that is the space and time swap stated exactly. The coefficient in front of dt flips positive. The coefficient in front of dr flips negative. Remember that sign flip. We will come back to it because it is the quiet hinge on which this entire topic turns. Here is a question that should be bothering you already. If space and time swap at that radius, does that mean the Schwarzschild radius itself, the event horizon, is where the disaster happens? Is the horizon the singularity? No, and this is one of the most important corrections in all of black hole physics. The event horizon is not a singular place. Nothing about the geometry actually breaks there. It only looks broken because the coordinates chosen in 1916 happened to misbehave at that radius, the way the lines of longitude on a globe all crowd together and become useless at the North Pole, even though the North Pole is a perfectly ordinary patch of ice. Sail across it and nothing happens. The crisis is in the map, not the territory. How do we know the horizon is only a bad map problem and not a real edge? Because you can draw a better map. In the late 1950s, David Finkelstein, building on a coordinate Arthur Eddington had written down decades earlier, rewrote the geometry using what is called an advanced null coordinate. He labelled events by the light rays falling inward rather than by clocks sitting far away. In those coordinates, the horizon turns smooth. Nothing diverges. An astronaut crossing it feels nothing special at the moment of crossing. No war, no flash, no jolt. Then, in 1960, Martin Kruskal and George Sgr A went further and built the maximal map, the one that shows the whole geometry at once, inside and out. And here is what the Kruskal and Sgr A map reveals, the single clearest demonstration in the subject. When you draw the black hole in their coordinates, the event horizon becomes a pair of straight diagonal lines. But the singularity, r equals 0, is not a dot at the middle of the picture. It is a curve stretched across the top of the diagram, running horizontally, lying in the future. In their coordinates, the singularity sits on the mathematical condition that the product of the two null coordinates equals 1. And geometrically, that is a space-like boundary lying across everyone's future. Read that again. The singularity is drawn not as a place in the middle, but as a horizon in time, a line that every future-pointing path must eventually cross, the way every life must eventually cross into next year. Picture a valley where the ground tilts more steeply the deeper you walk. Near the rim, you can still stroll sideways along the slope. A little deeper, the tilt is enough that walking sideways turns hard. Deeper still, the slope grows so severe that no matter which way you face, you are sliding downhill. Sideways is no longer available. There is only down. The light cones inside a black hole do exactly this. A light cone is the set of directions you are physically allowed to move, the fan of futures open to you at each instant. Far from the hole, that fan points evenly toward the future and lets you wander in space. Approaching the horizon, the whole fan tips inward, and once inside, the fan has tipped so far that every single direction it contains points toward smaller r. Every future you're allowed to have is a future closer to r equals 0. What does it mean that every allowed direction points the same way? It means that inside the horizon, moving toward the singularity is not a choice you make, it is the only kind of moving there is. Now let me answer the question buried in the hook, because it is one of the strangest facts in physics, and it falls straight out of this picture. If reaching r equals 0 is like reaching a moment in the future, how long do you have? And can you buy yourself more time? The maximum proper time, the longest life you can possibly experience, from crossing the horizon to arriving at r equals 0, for a radial freefall, is given by a beautifully compact formula. Tau max equals pi over 2 times rs over c. That is, half of pi multiplied by the Schwarzschild radius divided by the speed of light. Nothing else, just the size of the hole and the speed of light. For a black hole 30 times the mass of the Sun, that works out to about 197 millionths of a second. Andrew Hamilton at the University of Colorado computed this figure. Less than a heartbeat. For Sagittarius A star, the 4 million solar mass hole at the center of our galaxy, it stretches to roughly a minute. For M87 star, 6.5 billion solar masses, it becomes a matter of hours. But here is the part that overturns intuition. Because r has become a time direction, struggling against it is like struggling against time itself, and it backfires. If you fire your rockets and thrust away from the center, you do not extend your life, you shorten it. The longest survival is achieved by doing nothing at all, by falling freely, relaxed, making no effort to resist. The astronaut who fights, who burns fuel trying to climb back toward the horizon, reaches r equals 0 sooner than the astronaut who simply lets go. Think about what that means. In ordinary life, running from something can buy you time. Inside a black hole, running toward the future faster is the only thing your effort can accomplish. And effort in any direction is effort toward the end. The calm passenger outlives the panicked one. I return to this fact often, not because it is grim, but because it is so precisely, mathematically the opposite of everything our bodies are built to assume. Let me ground all of this in something real, because so far it could sound like pure abstraction. We have never seen inside a black hole. We never will, and I will come back to why. But we have now seen the outsides of two of them with extraordinary precision. On the 10th of April 2019, the Event Horizon Telescope collaboration released the first image of a black hole, M87 star, at the heart of the galaxy Messier 87, about 55 million light-years away. Its mass is 6.5 billion times the mass of the Sun. The image showed a ring of light, superheated gas, glowing orange and white, swirling around a central darkness, with a diameter measured at 42 micro-arcseconds across the sky, an angle so small it is like measuring a donut on the surface of the Moon from Earth. Then, on the 12th of May 2022, the same collaboration released the image of Sagittarius A star, our own galaxy's central black hole, 4.3 million solar masses, 27,000 light-years away. As the project scientist Jeffrey Bauer put it, they were stunned by how well the size of the ring agreed with the predictions of general relativity. And 4 years before the first image, on the 14th of September 2015, the LIGO detectors caught the gravitational waves from two black holes spiraling together and merging, the signal known as GW150914. The ripple in space-time matched the predicted waveform of two horizons becoming one. So the exterior geometry, the horizons, the masses, the shapes, is no longer theory. It is measured, photographed, and confirmed. Keep that firmly in mind, because it sharpens the mystery rather than dissolving it. Everything we can see confirms the theory magnificently, and the theory, applied to the region we cannot see, predicts its own breakdown. So what actually happens as you approach r equals 0 according to the classical theory? What is physically there in the moment you arrive? Classically, the answer is infinite tidal force. To measure whether a geometry is truly singular, as opposed to merely badly mapped, physicists compute a quantity called the Kretschmann scalar, which captures the real, coordinate-independent curvature of space-time. For the Schwarzschild geometry, it is simply k equals 48g squared m squared divided by c to the fourth r to the sixth. Notice the r to the sixth in the denominator. At the event horizon, Rs, this quantity stays perfectly finite. More proof that the horizon is not singular. But as r goes to 0, the curvature climbs without bound. It diverges. Divide by a number shrinking to nothing, and the result races to infinity. That is what true singularity means. Not a bad map, but a genuine, unbounded spike in the curvature of spacetime. What would infinite curvature do to a body? It would stretch you along one axis and crush you along the others, harder and harder without limit. The tidal force, the difference in gravity's pull between your head and your feet, grows so extreme that long before r equals 0, in a stellar mass hole, you are pulled into a thin stream of atoms. Physicists call it spaghettification, and it is not a metaphor for something gentle. What does it mean that a formula this simple 48 over r to the sixth, describes the total dissolution of anything that reaches it. It means the theory is describing its own edge. Because here is the honest reading, and it is the reading that opens the entire second half of this story. When a physical theory predicts that a real, measurable quantity becomes infinite, that is almost never nature announcing a genuine infinity. It is the theory raising its hand and admitting it has left the region where it applies. An infinity in your equations is a signpost that reads, "Something you neglected has become important here." And there is one thing general relativity neglects completely. It knows nothing of quantum mechanics. That brings us to the man in the hook, and to the theorem that made this a crisis no one could wave away. For decades, physicists had a comforting escape route, and I want you to feel how reasonable it was before I take it away. In 1939, J. Robert Oppenheimer and Hartland Snyder published the first real model of a star collapsing into a black hole, a paper titled "On Continued Gravitational Contraction." They took a perfectly round, perfectly uniform ball of matter and let gravity crush it, and out came a central singularity at r equals 0. But that same October, Einstein himself argued that Schwarzschild singularities do not exist in physical reality. And the escape route everyone leaned on was symmetry. The Oppenheimer and Snyder collapse was perfectly spherical. Real stars are lumpy, spinning, turbulent. Surely, the reasoning went, in a realistic, messy collapse, the infalling matter would not all converge on a single mathematical point. It would swirl, miss, form some complicated but finite structure. The singularity, in this hopeful view, was an artifact of assuming impossible perfection. The way a perfectly balanced pencil could, in principle, stand on its tip forever, but never does in the real, jostling world. So the question of the era was sharp and clear. Is the singularity a fragile consequence of unrealistic symmetry? Or is it robust, something that forms no matter how messy the collapse? In 1965, Roger Penrose answered it, and the answer was robust. His paper, Gravitational Collapse and Space-Time Singularities, ran barely 3 pages, and it changed the field permanently. Penrose did something nobody had thought to do. Instead of tracking matter and asking where it piles up, he studied the light. And he introduced a new idea, the trapped surface. What is a trapped surface? Picture flashing a spherical shell of light outward from a point, like the expanding surface of a soap bubble. In ordinary space, the outgoing wavefront grows, its area increases, while an ingoing wavefront shrinks, perfectly normal. Now picture a region where gravity grows so intense that even the outgoing wavefront shrinks. Both the ingoing light and the outgoing light are converging, losing area, being funneled inward. That is a trapped surface, a closed two-dimensional surface where both families of light rays, in and out, are contracting. Inside a black hole's horizon, every sphere is a trapped surface. Even the light you send outward is falling inward. Hold that image. Light itself, thrown outward as hard as physics allows, still losing ground. The engine underneath Penrose's proof is an equation written a decade earlier in 1955 by the Indian physicist Amal Kumar Raychaudhuri. It is called the Raychaudhuri equation, and for a family of light rays it reads d theta by d lambda equals minus 1/2 theta squared minus shear squared plus twist squared minus the Ricci curvature contracted with the light ray's direction. Let me translate. Theta is the expansion, whether the bundle of light rays is spreading out or converging. Lambda is a parameter marching you along the rays. Shear is how the bundle gets distorted in shape. Twist is how it rotates. And the final term is how matter and energy through space-time curvature bend the rays. Now look at what the equation forces. If the light rays are not twisting, and for the wavefronts Penrose considered they are not, then the twist term vanishes. Shear squared is always positive, so with a minus sign in front, it only ever helps convergence. And as long as energy is not negative, a condition physicists call the null energy condition, which ordinary matter always satisfies, that last term also drives convergence. Strip it down, and you are left with d theta by d lambda is less than or equal to minus 1/2 theta squared. Integrate that simple inequality, and something inescapable appears. 1/theta is greater than or equal to 1/theta initial plus lambda/2. If the rays start out converging, if theta begins negative, which is precisely the defining property of a trapped surface, then theta must plunge to negative infinity within a finite stretch of the parameter, specifically within lambda less than or equal to 2 divided by the size of that initial convergence. What does theta reaching negative infinity mean physically? It means the light rays are focused to a point, a caustic, where they cross and the bundle collapses to zero cross-section. Once you have a trapped surface, gravitational focusing guarantees the rays run into a caustic in finite time. There is no escaping it, no clever lumpiness that saves you, because the argument never assumed symmetry. It assumed only that a trapped surface exists and that energy is not negative. And that is the heart of the theorem. Penrose proved that if space-time contains a trapped surface, and energy behaves normally, and the geometry is reasonable in a technical sense, then space-time must be, the phrase is, geodesic incomplete. Paths simply end. A ray or a falling body traces its route, and then, in finite time, the route stops. Not because it hits a wall, but because space-time has no next point to offer. The path runs out of future. Here is the subtlety that almost every popular account gets wrong, and it is load-bearing for everything that follows, so hold on to it. Penrose did not prove that curvature becomes infinite. He proved that paths end, that space-time is incomplete. Geodesic incompleteness and infinite curvature are not the same statement. Remember that distinction. When we get to quantum gravity, the entire question will turn on the gap between the classical paths end and there is genuinely an infinity there. The power of the result lives in how little it assumes. Penrose did not need a round star. He did not need a still star. He needed a trapped surface and normal energy, and out came the inevitability of an ending. A small perturbation of a trapped surface is still a trapped surface, and that is what makes it robust. And in 1991, the mathematician Demetrios Christodoulou closed the remaining gap by proving that trapped surfaces actually do form from generic, non-symmetric, realistic collapse. The escape route was gone. Lumpy, spinning, turbulent, it did not matter. Collapse makes trapped surfaces, and trapped surfaces make endings. The physics community recognized what this meant, though it took time. In 2020, Roger Penrose was awarded half of the Nobel Prize in Physics, as the citation read, for the discovery that black hole formation is a robust prediction of the general theory of relativity. The other half went jointly to Reinhard-genzel and andrea-ghez for tracking the orbits of stars around the invisible massive object at the center of our galaxy, the very object the Event Horizon Telescope would later photograph. The Nobel Committee called Penrose's 3-page 1965 paper the most important contribution to general relativity since Einstein himself. Consider what that says. Not the most important since some minor figure, since Einstein, for a proof about where paths end. So let us take stock of where the classical theory has brought us, because it is a strange and precise place. The signature flip is settled mathematics. Inside the horizon, R becomes timelike, and the singularity becomes a moment. The light cone tipping is settled. Every future points inward. The Penrose theorem is settled. Trapped surfaces force spacetime to be incomplete, robustly, without any assumption of symmetry. And the Kretschmann scalar is settled. In the idealized Schwarzschild solution, curvature diverges as R goes to 0. Each piece is rigorous, uncontested, textbook. And yet, the sum of these settled pieces is a theory pointing at its own failure. This is the part that stays with me. Not any single result, but the way they combine into an honest confession. General relativity, our most beautifully confirmed theory of gravity, confirmed to exquisite precision by the EHT images, by LIGO, by the orbits Genzel and Ghez tracked, uses all that precision to tell us, calmly, that there is a place it cannot describe. It computes its own edge and hands us the coordinates of its own ignorance. Now I want to go deeper into what the approach to R equals 0 actually looks like, because I have been giving you a smoothed picture, and the reality, still within classical physics, is far stranger and more violent than a simple squeeze to a point. For a long time, physicists imagined the final approach to the singularity as monotonous, a steady, escalating crush, tidal forces growing smoothly until the end. But in 1970, 3 Soviet physicists, Vladimir Belinsky, Isaac Kalatnikov, and Yevgeny Lifshitz, worked out what a generic approach to a space-like singularity really looks like. And it is nothing like a steady crush. Their result is known by their initials, the BKL conjecture, and it describes chaos. Why should the approach be chaotic rather than smooth? Here is the reasoning. Near the singularity, BKL argued, 3 things happen. First, the dynamics become ultra-local. Each tiny patch of space evolves independently of its neighbors, because the violent time changes near the singularity outrun any signal trying to cross space. Second, the matter content stops mattering. Pure gravity dominates. And third, and most strikingly, each little patch of space begins to oscillate. Let me unpack the oscillation, because it is the eerie part. Each point evolves like a miniature universe of a specific type, a model that Charles Meisner in 1969 named the Mixmaster universe, after a brand of kitchen blender because of the way it churns. In a Mixmaster geometry, space stretches along some axes while contracting along others. Picture a lump of dough, squashed flat in one direction, squeezed thin in another, pulled long in the third. Then, and this is the chaos, the axes switch. The direction that was stretching starts crushing. A direction that was crushing starts stretching. Then they switch again, and again, faster and faster, in a sequence physicists call Käsner epochs, grouped into Käsner eras, with a jump from one era to the next governed by a chaotic map, the kind of mathematics where the tiniest change in starting conditions leads to wildly divergent outcomes. What would this do to a body falling in? Forget the clean image of being stretched steadily into a noodle. In a BKL approach, you would be stretched along one axis and crushed along the others, and then, before you could even register it, the axes would swap, and you would be crushed where you had been stretched and stretched where you had been crushed. Over and over, faster and faster, the pattern never settling, oscillating chaotically as r goes to 0. It is less like being squeezed and more like being kneaded by space-time itself in a rhythm that accelerates without limit and never repeats. For decades, this was a conjecture supported by pen and paper analysis and later by numerical simulation. Persuasive, but not proven. Then something remarkable happened very recently. In 2024, 3 physicists, Sean de Klerk, Sean Hartnell, and Jorge Santos, published a paper titled Mixmaster Chaos in an ADS black hole interior. Working in a particular class of spacetimes, they constructed black holes whose interiors explicitly realize the BKL and Mixmaster chaos, reducing the full evolution to a manageable set of equations. And they found a striking quantitative signature. The volume of the interior geometry collapses doubly exponentially over each Käsner era. Not exponentially, doubly exponentially, a rate so steep it is hard to hold in the mind, a shrinking of a shrinking. When they took the late-time dynamics and quantized them, they found the chaos connects to deep structures in pure mathematics. The modular group, random matrix statistics, a kind of order hiding inside the disorder. In 2026, others extended the same Käsner-era into era chaos to 5-dimensional black holes, governed by the geometry of what are called hyperbolic billiards. I find something worth pausing on here. The interior of a black hole is the one region of the universe we can never observe. And yet, physicists can characterize its chaos so precisely that they can connect it to the statistics of random matrices and the structure of the modular group. We are doing detailed physics about a place from which no report will ever return. Take a moment with that before we go further. But notice, and this is a foreshadowing I want you to file away, BKL describes the approach to the singularity. It describes the chaotic churning on the way down. It does not tell us what replaces the singularity, because it is still entirely classical. It is the most sophisticated possible description of general relativity driving toward its own breakdown. It makes the cliff edge more detailed and more violent. It does not build a bridge across it. For the bridge, we have to leave classical physics entirely. So let us ask the question the whole subject has been circling. If the infinity at r equals 0 is general relativity confessing that it has neglected quantum mechanics, then what does the quantum theory say happens instead? What is really there when the classical paths end? Now, I have to be honest with you about the ground we are standing on, because this is where certainty ends and candidates begin. There is no experimentally confirmed theory of quantum gravity. None. Everything I'm about to describe is mathematically motivated, internally serious, pursued by first-rate physicists and untested by any measurement. I will present the leading ideas fairly and neutrally as they are, and I will not pretend any of them is established. Keep the honesty of that in mind through everything that follows. The most developed program for resolving the singularity comes from a theory called loop quantum gravity. To understand what it does to the singularity, you have to understand its single most radical claim, that space itself is not smooth, that it comes in indivisible pieces. Why would anyone claim space is grainy? Think about how quantum mechanics changed our picture of everything else. Before quantum theory, energy seemed continuous. A heated object could glow with any amount of energy at all. Quantum mechanics revealed that energy comes in discrete packets, quanta, and this discreteness resolved paradoxes that had made the continuous picture predict impossible infinities. Loop quantum gravity takes that lesson and applies it to geometry. What if area and volume, like energy, come in discrete packets? What if there is a smallest possible patch of area, a smallest possible chunk of volume, below which the very notion of smaller stops making sense? In the mid-1980s, Abe-Ashtekar found a way to rewrite Einstein's theory of gravity in new variables, reformulating the geometry of space-time in terms of objects more like the fields of particle physics. And in 1994 and 1995, Carlo Rovelli and Lee Smolin used this reformulation to compute something astonishing. They found that in loop quantum gravity, the area of any surface cannot take just any value. It is quantized. The allowed areas are given by the formula A equals 8 pi gamma times the Planck length squared times a sum over the surface of the square root of j times j plus 1, where each j is a quantum number that can be 1/2, 1, 3/2, and so on. Gamma is a fixed number called the barbero-immirzi parameter, roughly 0.24, and the Planck length is the almost inconceivably small scale, about 1.6 times 10 to the minus 35 meters, where quantum gravity must take over. The consequence that matters for us is this: there is a smallest non-zero area. The theory calls it the area gap, and its value is 4 times the square root of 3 times pi times gamma times the Planck length squared. Numerically, about 5.17 Planck areas. Below the area gap, there is no smaller area. It is not that we cannot measure smaller, it is that in this theory, smaller does not exist. The states of geometry themselves are built from networks. Physicists call them spin networks. Graphs whose edges carry those quantum numbers and whose structure is the fine-grained atomic makeup of space. Now do you see what this does to the singularity? The classical catastrophe was geometry shrinking to zero. Zero volume, infinite density, infinite curvature. But if there is a smallest possible chunk of area and a smallest possible chunk of volume, then geometry cannot shrink to zero. It cannot, because zero is smaller than the smallest allowed thing. The atomic structure of space, if it is real, would refuse to collapse to a point, the way the electrons in an atom refuse to spiral into the nucleus. Quantum mechanics simply does not permit the endpoint that the classical theory demanded. To see what that refusal looks like dynamically, physicists turned first to an easier arena than a black hole: the entire universe. Applying loop quantum gravity's methods to cosmology, to the expanding universe as a whole, produced a field called loop quantum cosmology. And its central result is stunning. In 2001, Martin Bojewald showed that in loop quantum cosmology, the Big Bang singularity is absent. And in 2006, Abhay Ashtekar, Tomasz Pawlowski and Parampreet Singh made it precise with an exactly solvable model. They derived a modified version of the equation that governs the expansion of the universe. The ordinary Friedmann equation says the expansion rate squared is proportional to the density. Their corrected version reads h squared equals 8 pi g over 3 times rho times the quantity 1 minus rho over rho critical. Look at that final factor, 1 minus rho over rho critical, because that is where the magic lives. In the classical theory, as you run the universe backward toward the Big Bang, the density rho climbs toward infinity and the equations shatter. But in the corrected equation, as rho climbs toward rho critical, that factor drops toward zero and then negative. The expansion rate is driven to zero and reverses. The contraction halts and rebounds. The singularity is replaced by a bounce. And they computed the critical density where it happens. It is rho critical equals the square root of 3 divided by 32 pi squared gamma cubed times the Planck density, which comes out to about 0.41 times the Planck density. Now, the Planck density is a number almost beyond comprehension, about 5 times 10 to the 96th kilograms per cubic meter, 10 to the 93rd grams in a single cubic centimeter. So the bounce in this model happens not at infinite density, but at roughly 41% of the Planck density. Sub-Planckian, yes, but still an almost unimaginably vast concentration of matter. Finite. Enormous, but finite. What does it mean that the bounce is triggered by density and not by size? This is the subtle, crucial point. The rebound is set off when the energy density, the curvature, hits its ceiling, not when space shrinks to some tiny volume. Which means the bouncing region can be far, far larger than the Planck length. It is the concentration that matters, not the smallness. Hold that thought, because it is exactly what makes the next idea physically plausible rather than absurd. Here is where honesty requires a caveat, and I will give it its full weight rather than bury it. The clean bounce I just described is rigorously established in the simplest case, a smooth, uniform, isotropic universe with a single, simple field. A black hole interior is not that. It is anisotropic, squeezed differently along different axes, exactly the Mixmaster churning we met earlier. And Bojewald himself, in 2008, published a pointed internal critique, warning that a consistent combination of quantum geometry effects rules out a large class of these models, and that, in his words, no model of the Schwarzschild black hole interior analyzed so far was fully consistent. This is not a skeptic outside the field throwing stones. This is one of the founders of loop quantum cosmology holding his own program to account. I want you to see that the disagreement here is internal, rigorous, and healthy, not a sign the whole enterprise is empty, but a sign of how hard the real problem is. Still, the program pressed forward to the black hole case directly. In 2018, Abhay Ashtekar, Javier Olmedo, and Parampreet Singh published what they called a quantum transfiguration of the kruskal spacetime, an effective loop quantum description of the full black hole geometry inside and out. And their result is a concrete, equation-level answer to what replaces the singularity. In their model, the singularity is gone, and in its place is a space-like transition surface, a surface of finite, non-zero size that separates a trapped region, which behaves like a black hole, from an anti-trapped region, which behaves like a white hole, the time reverse of a black hole. And crucially, the curvature, that Kretschmann scalar which classically raced to infinity, is bounded. It hits a maximum, a universal ceiling at the Planck scale, and it is the same ceiling regardless of the black hole's mass. Near the horizon of a large black hole, their quantum corrections are utterly negligible. So the theory agrees with general relativity exactly where general relativity is confirmed. Bojewald and others promptly published critiques of the model's behavior far from the whole. Again, the internal argument continues. But the shape of the claim is clear. Where classical physics put an infinite spike, this model puts a finite bridge, and on the far side of that bridge is a white hole. That word, white hole, brings us to the boldest version of this whole family of ideas, and I want to present it carefully because it is real physics done by serious people, and it is also explicitly a minority view. Its proponents say so themselves. In 2014, Carlo Rovelli and Francesca Vidotto proposed the Planck star. The idea is a direct extension of the bounce. Collapsing matter, they argued, does not crush to a singularity. When its density reaches the Planck scale, a quantum pressure arising from the discreteness of geometry halts the collapse and triggers a rebound, just like the cosmological bounce. And because, as we established, the trigger is density rather than size, the resulting core can be enormously larger than the Planck length. How large? For a black hole of stellar mass, they estimated a core about the size of a proton, roughly 10 to the minus 14 centimeters. That is around 20 orders of magnitude larger than the Planck length. A proton-sized object holding the mass of a collapsed star. Think about the compression, the mass of something larger than the Sun, held in a volume smaller than a single atom. Yet still, by the standards of quantum gravity, gigantic. Then, in 2015, Hal Haggard and Carlo Rovelli went further and wrote down an explicit geometry. They called it, memorably, black hole fireworks. It describes matter falling in, reaching the bounce, and then emerging from a white hole. And here is its elegant feature. Their metric satisfies Einstein's classical equations everywhere except within a small, compact region, a quantum tunneling zone, right around where the singularity would have been. Everywhere else, ordinary general relativity holds. The quantum weirdness is quarantined to the tiny region where it is genuinely needed. A black hole in this picture is not a permanent grave. It is a phase, a very long pause in a process that ends with the trapped matter tunneling back out through a white hole. And now, the strangest number in the entire subject, the one I promised at the start. How long does this black to white tunneling take? In 2016, and again in 2024, Marios Christodoulou, Carlo Rovelli and their collaborators computed it using the full machinery of loop quantum gravity, the spin foam amplitudes, the quantum sum over geometries. And they found two utterly different timescales. The crossing time, the time the bounce itself takes, scales linearly with the mass, quite short. But the lifetime, the time you would have to wait for the tunneling to actually occur, controlled by quantum probability, scales as the mass times e raised to a factor times the mass squared, an exponential of the mass squared. For anything of astronomical mass, that is a duration so vast it dwarfs the current age of the universe many times over. Here is what makes it dizzying. Because of the extreme gravitational time dilation, that same process, which takes longer than the age of the cosmos as seen from outside, could be nearly instantaneous for the infalling matter itself. From the star's own point of view, fall in, reach the bounce, bounce, come back out, a flash. From our point of view out here, a wait longer than the universe has existed. The same event, one clock reading an instant, another reading an eternity. What does it mean that a single physical process can be a heartbeat and an eternity at once, depending only on where you stand? It means gravitational time dilation, which we have measured in laboratories and in orbiting clocks, taken to its logical extreme, dissolves the very notion of how long did it take into a question with no single answer. I want to be scrupulously fair here. This is a minority program. The physicist Sabine Hossenfelder, among others, has published skeptical analyses questioning whether Planck stars can exist as described. The proposed observational fingerprints, that Planck star bounces might produce fast radio bursts or gamma-ray signals, that ancient white hole remnants might make up some of the dark matter, remain entirely unconfirmed. This is frontier physics, actively pursued, honestly contested. I present it because it is real and serious, not because it is settled. It is not. There is one more piece of the puzzle, and it is the genuine exception to everything I have told you. The case where the singularity really is, in a sense, a place. I told you at the very beginning that the clean moment, not a place statement is exact for the non-rotating black hole. But real black holes spin, every one of them, and spin changes the story. A rotating black hole is described not by Schwarzschild's 1916 solution, but by a solution Roy Kerr found in 1963. And in the Kerr geometry, the singularity is not a point, and not a space-like moment. It is a ring, a circle, lying in a plane at r equals 0. And it is timelike, not spacelike. Remember how inside a Schwarzschild hole, the light cones tip over so that every future points at r equals 0. In a Kerr hole, there are two horizons, an outer one and an inner one, called the Cauchy horizon. The cones tip over as you cross the outer horizon, but as you cross the inner one, they tip back. Space and time resume their ordinary roles. And that means the ring singularity becomes something you could, in the idealized mathematics, avoid. You could steer around it. You could, in principle, even pass through the ring into a region where the equations permit paths that loop back into their own past. So, in the rotating case, the singularity really is a place, a ring you could point to and dodge. This is the genuine mathematical exception, and I will not pretend it away. But, and here the story takes its final turn, that idealized picture may be an illusion of perfection, in exactly the way the old spherical collapse argument was an illusion of perfection. Here is the problem. Beyond that inner Cauchy horizon, general relativity loses the ability to predict the future. The equations admit infinitely many equally valid continuations. Determinism, the bedrock principle that the present fixes the future, simply fails. Roger Penrose found this so troubling that in 1969 he proposed what he called cosmic censorship, asking, in his own words, whether there exists a cosmic censor who forbids the appearance of naked singularities, clothing each one in an event horizon. The strong version of the conjecture holds that this breakdown of determinism at the Cauchy horizon is not physical, that in any realistic black hole, generic disturbances should pile up at the Cauchy horizon and turn it into a genuine barrier, sealing off the pathological region and restoring determinism. For decades, this was debated. Then came a sequence of deep mathematical results that I want to lay out because they are a model of how honest science refines a hard question. In 2017, Mihalis Stafermos and Jonathan Luke proved something surprising. For realistic data settling down to a Kerr black hole, the metric actually extends continuously across the Cauchy horizon. It does not simply end there. This disproved the strongest form of cosmic censorship, the version claiming the metric itself must terminate. An observer reaching the Cauchy horizon is not instantly annihilated. The geometry is continuous. That was a genuine surprise, and it cut against decades of expectation. But the story did not end there, and this is the reconciliation. Luke and Songjin Oh, and later Jan Spiersky and others, showed that while the metric is continuous at the Cauchy horizon, its curvature is not well behaved in a subtler, integrated sense. The derivatives blow up. Tidal distortions diverge when you add up their effects. The technical statement is that a refined version of cosmic censorship, the version demanding the geometry cannot be extended as a suitably smooth solution, holds true. So, the Cauchy horizon is what physicists now call a weak null singularity. The metric is continuous. You are not instantly destroyed the moment you reach it, which overturns the old picture, but the curvature diverges in an accumulated way, which supports the modern picture. And the upshot for our ring singularity is this. The idealized, smooth passage around the Kerr ring, the clean, avoidable place, is believed to be an artifact of perfect symmetry, destroyed by generic perturbations, just as the spherical collapse escape hatch was destroyed by Penrose in 1965. Reality, it seems, keeps closing the doors that idealized mathematics leaves open. Now let me bring these threads together, because we have laid out everything the evidence offers, and it is time to weigh it honestly and say what it actually shows. Earlier, I told you to remember the sign flip, the moment the metric coefficient changes sign at the horizon. Here is its payoff. That sign flip is not a quirk of one coordinate system or one physicist's preference. It is settled, uncontested, textbook mathematics. And it delivers the verdict promised in this video's title. In a non-rotating black hole, the singularity is not a point in space at the center. It is a moment in the future. The radial direction becomes timelike. R equals 0 becomes a time, not a place. And every path inside the horizon runs toward it as helplessly as your own life runs toward the next moment. On this, there is no scientific controversy whatsoever. If you take one thing from all of this, take that. The deepest, widely true fact about black holes is that inside them, down becomes later. Space becomes trajectory. Earlier, I also told you to remember that Penrose proved paths end, not that curvature is literally infinite. Here is that payoff. The singularity theorems are rock solid. They prove, with minimal and robust assumptions, that classical general relativity leads inescapably to geodesic incompleteness. Paths end. That much the evidence fully supports. But the theorems do not prove that a genuine physical infinity sits at the end. And the near-universal judgment of physicists, including Ashtekar, who put it plainly that this limitation of general relativity comes from the fact that it ignores quantum mechanics, and Hawking, who wrote that at the singularity the laws of science break down, is that the infinity is not the last word. It is the theory announcing where it must hand off to a deeper one. So which explanation does the evidence support? Let me weigh them as fairly as I can. Classical general relativity, predicting a true singularity, is confirmed magnificently everywhere we can test it. The EHT images, the LIGO mergers, the tracked stellar orbits. And it robustly predicts, via Penrose, that paths end inside. Its strength is overwhelming empirical success. Its weakness is fatal and self-declared. At R equals 0, it predicts infinities, which is a theory diagnosing its own breakdown, not describing a real place. The BKL and Mixmaster picture refines the classical approach into detailed chaos, now with explicit numerical realizations from the 2024 de Klerk-Hartnoll-Santos work, but it too is classical. It describes the road to the cliff, not what lies beyond it. The loop quantum gravity resolutions, the bounce, the AOS transition surface, the Planck star, offer a concrete, finite replacement for the singularity, mathematically motivated and internally serious, and they resolve the infinities in principle. But they are contested even from within, as Bojewol's own critiques show, and, this is decisive, not one of them has any experimental confirmation. And the Kerr timelike ring, the genuine exception, appears on close mathematical examination to be smoothed away by generic perturbations into a weak null singularity, thanks to the de Fermos, Look and Luke O results. Here is where the evidence honestly lands. Two things are settled. The role reversal is real. In the non-rotating case, the singularity is a moment, not a place. This video's central claim, and it is uncontested. And the singularity is almost certainly not the final word. Expert judgment holds, on strong theoretical grounds, that quantum gravity intervenes before any true infinity is reached. But one thing is genuinely open, and I will not close it, because the evidence does not. We do not know what actually replaces the classical singularity. The bounce, the transition surface, the Planck star, the fireworks, each is a beautiful, serious, mathematically motivated candidate. Not one is tested. And here is the cruelest part of the whole subject, the reason this particular ignorance may be permanent. The one place the answer lives is the interior of a black hole, and the interior is causally sealed. No signal, no light, no probe, no report ever crosses back out through the horizon. We can compute what might be in there in exquisite detail. We can connect its chaos to the modular group and its curvature to the Planck scale, but we can never send anything in to look and hear back what it found. It is the one frontier we can calculate and never visit. That is the honest edge. And I want to state exactly where it sits because it is easy to overreach in either direction. The science resolves what it can resolve: the geometry, the role reversal, the inevitability of the classical ending, the strong expectation of a quantum resolution. Where the science reaches its limit is the question of what is truly there at the end. And beyond even that, the deeper question of why any of this structure exists at all. Why there is a universe with laws that produce black holes and horizons and edges to knowledge. Those questions lie past what any measurement can settle. The equations break down at the singularity, and it is honest to say so plainly, and to leave that question standing open, rather than answering it with more confidence than the evidence permits. Now I want to go deeper into the story of how physicists came to accept any of this, because it explains why the moment not a place picture took half a century to become common knowledge, and why so many popular diagrams still get it wrong. Carl Schwarzschild found his solution in 1916, within months of Einstein publishing General Relativity, and he did it under conditions that ought to be remembered. He was a German artillery officer serving on the Russian front in the First World War, computing the exact geometry of space-time around a spherical mass between military calculations, already ill with the autoimmune disease that would kill him within the year. He mailed his solution to Einstein, who presented it to the Prussian Academy on his behalf. Einstein was astonished that an exact solution existed at all. He had expected only approximations. And, buried inside that exact solution, were the two features that would haunt physics for a century: the radius, where the metric coefficient misbehaves, and the point at r equals 0, where the curvature genuinely explodes. For decades, almost no one took the interior seriously. Why would they? The Schwarzschild radius of any ordinary object lies buried deep inside it, in a region where his vacuum solution does not even apply. The Sun's is under 2 miles, tucked inside a body 800,000 miles across. To reach the strange geometry, you would need to compress matter to absurd densities, and no one knew a mechanism that could do it. The interior looked like a mathematical curiosity, a region the universe would never actually build. What changed that? Stellar death changed it. In the 1930s, Subrahmanyan Chandrasekhar showed that a white dwarf star cannot exceed about 1.4 times the mass of the Sun before the quantum pressure holding it up fails. Push past that limit and gravity wins. Then in 1939, Oppenheimer, working with George Volkoff, showed that even a neutron star, the next denser refuge, has its own upper mass limit. And that same year, in the paper we met earlier, Oppenheimer and Snyder followed the logic to its end. A massive star that exhausts its fuel and exceeds every limit has nothing left to stop it. It collapses. Not to a smaller star, but through the Schwarzschild radius all the way down. Suddenly, the interior was not a curiosity. It was the fate of every sufficiently massive star in the sky. The strange geometry became a place the universe manufactures routinely, by the billions. And still the confusion about what the interior is persisted, because the coordinates hid it. Think about what a coordinate system really is. It is a labeling scheme, an agreement about how to assign numbers to events. Schwarzschild's original labels used r as a radius and t as a time. And those labels feel natural because, far from the black hole, they behave exactly like the radius and time you know. The trouble is that a labeling scheme built to be sensible far away can quietly become nonsense up close. Picture a mapmaker who lays a grid over a flat plane, longitude and latitude running clean and square, and then extends that same flat grid over a mountain without ever looking up. On paper, the grid lines stay neat. In reality, they are climbing a cliff. The lines have not changed. What they describe has. Schwarzschild's T and R are those grid lines, and the horizon is the cliff the flat map refuses to show. This is why David Finkelstein's 1958 work mattered so much. He was not discovering new physics so much as drawing a better map, one whose grid lines followed the infalling light instead of the distant clocks. And the moment he did, the horizon revealed its true character, a one-way membrane. Things cross it inward and can never cross back out, not because of a war, but because on the far side, every future points deeper in. Finkelstein described it as a perfect unidirectional membrane, a surface causal influences cross in only one direction. That phrase captures the whole strangeness. The horizon is not made of anything. You could drift across the event horizon of a supermassive black hole and feel nothing at the instant of crossing. No barrier, no sensation, no marker. And yet, you would have passed a point of no return as absolute as the passage from today into tomorrow. Consider what that does to the experience of falling in. From the outside, watching a friend fall toward a black hole, you would never see them cross. Their image would slow, redden, dim, and freeze at the horizon. Their last instant smeared across eternity as the light climbing out fought the deepening gravity and lost. To you, they never arrive. But from their own perspective, nothing hesitates. They cross smoothly, feel no jolt at the horizon, and then have only their tau max seconds before r equals 0. Two accounts of one event, both correct, sharing no common answer to the simple question, did they cross and when? This is not a paradox to be resolved. It is the plain content of the theory. What does it mean that two honest observers cannot agree on whether an event has happened yet? It means simultaneity. The notion of a shared now is not a feature of the universe, but a local convenience. And near a black hole, even that convenience dissolves. There is a companion object to the black hole that we have mentioned, but not yet examined properly, and it deserves its own moment, because it is where several of these threads converge. The white hole. In the maximally extended Schwarzschild geometry, the full Kruskal and Sgr A map, there is not one strange region, but a mirror pair. The black hole is a region nothing can leave. Its time reverse, the white hole, is a region nothing can enter. Matter can only pour out of it. General relativity's equations are symmetric under reversing the direction of time. So if collapse to a black hole is a solution, then the reverse, an eruption from a white hole, is equally a solution. For most of the 20th century, white holes were dismissed as unphysical, a mathematical shadow with no counterpart in nature, because nothing in our universe seemed to make one. But notice where they reappeared in our story. At the far side of the loop quantum bounce, in the Ashtekar-Olmedo-Singh transition surface, separating a trapped region from an anti-trapped one, and in the black hole fireworks, where infalling matter tunnels out through a white hole. The white hole, long treated as a curiosity, becomes in these frameworks the natural second half of a black hole's life. What was a permanent grave becomes a chrysalis. Why should we take the possibility of a bounce seriously at all, rather than trusting the classical prediction of a true singularity? The strongest reason is a lesson physics has learned repeatedly. Whenever a classical theory has predicted an infinity, the quantum theory underneath has erased it. Consider the atom. In the classical picture of the early 20th century, an electron orbiting a nucleus should radiate away its energy and spiral inward, crashing into the nucleus in a fraction of a nanosecond, releasing infinite energy as its orbit shrank to zero. Matter as we know it should not exist. It was a genuine infinity, a genuine catastrophe sitting in the equations, and quantum mechanics dissolved it completely. The electron cannot spiral in because there is a lowest allowed energy state, a smallest allowed orbit, below which smaller is not a physical option. The infinity was not real. It was the classical theory being pushed past its domain. Loop quantum gravity's claim about the singularity is precisely this lesson applied to geometry itself. Just as there is a smallest orbit for an electron, there may be a smallest volume for space, and the collapse to r equals 0 may be as forbidden as the electron's death spiral. This is the analogy that makes the bounce feel less like wishful thinking and more like history repeating. But the analogy also carries a warning, and honesty demands I sound it. The reason we believe the atom's story is that we can measure it. The spectral lines, the energy levels, the stability of matter itself are all in front of us, tested to staggering precision. The reason the singularities story remains open is that we cannot measure it. The atom handed us evidence. The black hole interior hands us nothing but computation. That is the whole difference between a resolved question and an open one. And it is worth keeping the two firmly apart, even when the analogy between them is beautiful. There is a deeper puzzle threaded through all of this, one that gives the whole subject its urgency in the physics community. And it is worth stating plainly because it explains why so many brilliant people spend careers on a region no one can observe. It is the information paradox. In the 1970s, Stephen Hawking showed that black holes are not perfectly black, that quantum effects near the horizon cause them to radiate very faintly and slowly evaporate over immense spans of time. A black hole the mass of the Sun would take something like 10 to the 67 years to evaporate this way, vastly longer than the current age of the universe. But evaporate it does, in principle. And here is the paradox. If everything that fell in is crushed to a singularity, and then the black hole radiates away into featureless heat, then the detailed information about what fell in, which star, which books, which people, is erased from the universe entirely. And the erasure of information is something quantum mechanics flatly forbids. Quantum theory says information is conserved. The past is always, in principle, recoverable from the present. A true singularity that destroys information would break that law. So the two great pillars of physics, general relativity and quantum mechanics, collide most violently not at the horizon, but at r equals 0, over the fate of information. What does it mean that resolving what sits at the singularity might decide whether the past can be erased? It means the interior of a black hole is not a remote curiosity. It is where we find out whether the universe keeps a perfect record. This is exactly why a bounce, or a Planck star, or a white hole remnant is so appealing to its proponents. Not merely because it removes an ugly infinity, but because it offers a way for the information to survive. If the collapse rebounds rather than terminating, then what fell in is not destroyed. It is stored, transformed, perhaps eventually released. Carlo Rovelli, reflecting on why quantum gravity matters at all, described objects falling into a black hole as phenomena that fall outside the domain of both our great theories at once, and call that overlap a deep, profound gap in our fundamental picture of the world. The singularity is where that gap is widest. Resolve it, and you may resolve the information paradox in the same stroke. That is the prize, and it is why the interior of a region we can never enter is one of the most fiercely worked frontiers in theoretical physics. Let me return to the granularity of space, because I introduced the area gap quickly, and it rewards a closer look. It is where loop quantum gravity makes its most concrete, most checkable claim. And it is tied to something you can almost hold in your hand: the entropy of a black hole. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that a black hole has an entropy, and that its entropy is proportional to the area of its horizon. Specifically, 1/4 of the horizon area measured in Planck units. Written compactly, S equals A over 4 in those units. This was a shock. Entropy, everywhere else in physics, counts the number of microscopic arrangements a system can have, the number of ways of shuffling its atoms while keeping its overall appearance the same. So, if a black hole has an entropy proportional to its area, then its horizon must be built of some enormous number of microscopic pieces. And the count of those pieces must scale with area, not volume. What are those pieces? Loop quantum gravity offers a specific answer, and this is what makes it more than philosophy. In this theory, the horizon is punctured by the edges of the spin network. Each edge that pierces the surface contributes a discrete quantum of area given by that formula involving the square root of j times j plus 1. Count the ways those punctures can be arranged to build up a given total horizon area, and you get the entropy. And here is the constraint that makes it testable in principle. For the count to match the Bekenstein-Hawking value of exactly 1/4, the barbero-immirzi parameter, that number gamma sitting in the area formula, must take a specific value. Different ways of doing the counting yield gamma around 0.24 or around 0.27. And one classic derivation gives gamma equal to the natural logarithm of 2 divided by pi times the square root of 3. The theory is not free to choose. The entropy fixes the graininess of space. The same parameter that sets the smallest possible area also sets the critical density of the cosmological bounce, which is why ρ critical came out to that specific 41% of the Planck density, and not some arbitrary figure. One number, threaded through the entropy of horizons, the size of the area gap, and the density of the bounce. Whether that number is physically real remains unconfirmed. But the internal consistency, the way a single parameter locks together three seemingly unrelated results, is the kind of structure that makes physicists take a theory seriously, even before experiment can reach it. Now hold that granular picture against the smooth classical collapse and feel the collision. General relativity is built on the assumption that space-time is a perfectly smooth continuum, infinitely divisible, no smallest length. Its prediction of a singularity is the direct consequence of that assumption taken to the limit, smoothness all the way down to zero. Loop quantum gravity denies the premise. It says smoothness is an illusion of distance, the way a photograph looks continuous until you magnify it far enough to see the pixels, or the way a beach looks like a smooth tan surface from the boardwalk and resolves into distinct grains of sand when you kneel down. If space is pixelated at the Planck scale, then the classical collapse to a point is describing a resolution that does not exist, like insisting a digital image can be zoomed in forever. The singularity in this reading is an artifact of pretending the pixels are not there. Whether the pixels are really there is the open question. But you can see now why the two theories disagree so violently about r equals 0. They disagree about whether 0 is even a place the universe allows you to go. Let me anchor the sheer scales involved, because numbers this extreme lose their meaning unless we hold them against something. The Planck length, where quantum gravity must dominate, is about 1.6 times 10 to the minus 35 meters. How small is that? If you took a single hydrogen atom and blew it up to the size of the entire observable universe, the Planck length, scaled up by the same factor, would still be smaller than a grain of sand. That is the scale at which the area gap lives, at which the graininess of space, if it exists, would appear. And the Planck density, 5 × 10⁻96 kilograms per cubic meter, is the density you would get by packing the mass of 100 billion suns into the volume of a single atomic nucleus. These are not numbers we reach for drama. They are the numbers the theory hands us as the ceiling, the density at which the collapse in the loop quantum picture would rebound rather than continue. The bounce, when it happens at roughly 41% of that already unimaginable ceiling. And yet, this is the counterintuitive gift of the bounce being triggered by density rather than size. The bouncing region need not be small at all. Run the estimate for the cosmological case, and the volume at the bounce can exceed the Planck volume by some 75 orders of magnitude. Run it for a stellar mass black hole's Planck star, and you get a core the size of a proton, 20 orders of magnitude above the Planck length. Picture that proton-sized core holding the mass of a dead star heavier than the Sun. Then picture that the reason it does not collapse further is not that it has run out of room, but that it has run out of allowable density. It has hit the ceiling of how concentrated energy can become before geometry itself pushes back. Space is not resisting because it is full. It is resisting because, in this picture, there is a maximum to how sharply space-time can be curved, and matter has reached it. I want to give the chaotic approach one more pass as well, because the BKL and Mixmaster picture connects to something you have felt with your own body, and the connection makes the abstraction concrete. You know the sensation of tidal force already in miniature. It is why the moon raises tides on Earth. The near side of the Earth is pulled slightly harder than the far side, so the planet is stretched very gently along the Earth-Moon line, and the oceans bulge. That is a tidal force, not gravity itself, but the difference in gravity across an object. Near a black hole, the difference in pull between your head and your feet grows until it exceeds what your body can withstand, and you are stretched along the radial direction, the spaghettification we met. But the BKL result says the reality of the final approach is worse and stranger than a steady pull. The stretch axis and the crush axis do not stay fixed. They swap chaotically in the accelerating sequence of Kasner epochs. First, you are stretched head to foot and crushed side to side. Then, before you can register it, the pattern flips. Crushed head to foot, stretched side to side, and flips again and again, faster and faster, the switches piling up without limit as r equals 0 approaches. It is why I called it kneading rather than squeezing. Dough is not merely compressed, it is folded, turned, stretched, folded again, the deformation changing direction endlessly. The 2024 result that the interior volume collapses doubly exponentially over each Kasner era tells you how ferocious the pace becomes, a shrinking so rapid that even the word exponential undersells it. What does it mean that the most detailed classical picture of the singularity's approach is chaos rather than a clean crush? It means the classical theory, right up to the edge where it fails, is not simplifying, it is complexifying, generating ever finer, ever faster, ever more intricate structure as it drives toward the moment it can no longer describe. The road to the breakdown is not a smooth ramp, it is a fractal storm. And that makes the quantum resolution, if it exists, all the more remarkable a thing to imagine. Something that reaches into that accelerating chaos and, at the Planck ceiling, brings it to a halt and turns it around. Return once more to the rotating case, the Kerr geometry, because it holds the subtlety that most rewards careful thought, and I gave it only in outline. The reason a spinning black hole has two horizons rather than one comes from the mathematics of its metric. But the physical picture is graspable. Rotation resists collapse. The spin provides a kind of centrifugal effect that props the geometry open, creating an inner region the non-rotating hole does not have. Between the outer horizon and the inner Cauchy horizon, R is timelike, and you fall inexorably inward, exactly as in the Schwarzschild case. But cross the inner Cauchy horizon and R becomes spacelike again. You can stop, you can maneuver. The relentless fall is over. And there, floating in that innermost region, is the ring singularity, timelike, avoidable, a genuine place in a way the Schwarzschild moment never was. The mathematics even permits, in the idealized exact solution, paths that thread through the ring into a region where R takes negative values, a region containing closed timelike curves, world lines that loop back to their own past. Take that literally for a moment, and it means the idealized Kerr solution contains, buried in its innermost chamber, the mathematical possibility of returning to your own earlier self. This is the kind of result that makes physicists deeply suspicious rather than excited, because a theory that predicts you can meet your own past is a theory predicting the failure of cause and effect, and that is usually the signal that an idealization has been pushed past its validity. Which is precisely what the cosmic censorship program and the de Fermat's look and look-O theorems suggest is happening. The pristine Kerr interior, with its avoidable ring and its time loops, is the perfectly balanced pencil standing on its tip. The instant you perturb it, the instant you let a single realistic ripple of gravitational radiation fall in, the blue shift instability at the Cauchy horizon piles that radiation up into a diverging wall of curvature, and the smooth passage inward becomes a weak, null singularity. The pencil falls. The phrase for that pileup is mass inflation, worked out by Eric Poisson and Werner Israel in 1989, and the image behind it is worth holding. Anything that falls into the black hole after you, every photon, every stray particle, the accumulated light of the entire external universe's future, gets blue shifted to enormous energy as it races toward the inner horizon. Because, from the perspective of that horizon, the whole infinite future of the outside universe arrives compressed into a finite span. The effective mass parameter of the geometry inflates without bound. It is as if the Cauchy horizon collects the entire future history of the cosmos and slams it into a single instant. That collected, blue-shifted energy is what turns the smooth inner horizon of the idealized solution into a singular barrier in the real, perturbed case. So the determinism that the exact Kerr solutions seem to threaten is, in the end, protected, not by fiat, but by the physical mechanism of infalling radiation sealing the pathological region behind a wall of diverging curvature. Roger Penrose's cosmic censor in this reading is not a mysterious guardian, it is mass inflation doing its work. This is the pattern that repeats through the entire subject, and it is the pattern I find most striking. Every time the idealized mathematics offers an escape from the harshness of the singularity, a clever symmetry that avoids collapse, a ring you can dodge, a corridor to your own past, a more careful analysis, accounting for the messiness of the real world, closes it again. The Oppenheimer and Snyder spherical symmetry offered an escape. Penrose closed it with trapped surfaces. Kerr's ring offered an escape. Mass inflation and the c-squared cosmic censorship results appear to close it. The universe seems to guard the singularity jealously, permitting no idealized loophole to survive contact with reality. And yet, here is the twist that keeps the question open rather than closed. The one loophole that reality might genuinely permit is the quantum one. Not a clever coordinate trick, not a special symmetry, but the possibility that space itself is grainy and cannot collapse to zero. That loophole cannot be closed by adding more classical realism, because it does not live in classical physics at all. It lives below the Planck scale, in the regime where general relativity has already admitted it cannot speak. Which is exactly why it remains the live candidate when all the classical escapes have failed. Consider what we can and cannot say, laid side by side, because the honest map of our knowledge here is itself the payoff. We can say with full confidence that inside a non-rotating black hole, the radial direction is timelike and the singularity is a moment. This is settled geometry, checkable by anyone who works through the coordinates. We can say the singularity theorems hold. Trapped surfaces form in realistic collapse, and they force geodesic incompleteness. We can say the horizon itself is not singular, that the Kretschmann scalar is finite there and diverges only at r equals 0. We can say the areas and volumes of loop quantum gravity are discrete, given a specific set of assumptions, and that the loop quantum cosmology bounce is rigorous in its simplest model. These are the things the evidence and the mathematics genuinely establish. And then there is everything we cannot say. Which quantum gravity theory, if any, is correct? Whether the bounce survives in the anisotropic black hole case that Bojewald's critique targets? Whether Planck stars exist? Whether their signatures will ever be seen in a fast radio burst or a gamma-ray flash? Whether white hole remnants drift through the galaxy as dark matter? Whether information escapes? The line between these two lists is the exact border of human knowledge on this question. And it is a border drawn not by a lack of cleverness, but by a horizon that physically forbids the observation that would settle it. There is a reflection I keep returning to, and it is not about the physics so much as about the peculiar position it puts us in. We have imaged the shadow of a black hole. The Event Horizon Telescope turned the entire Earth into a single instrument and photographed the silhouette of M87 star against its own glowing gas, and then did it again for Sagittarius A star at the center of our own galaxy. We can measure the mass of these objects to a fraction of a percent by watching stars whip around them, as Reinhard-Genzel and andrea-ghez did for decades to earn their share of the 2020 Nobel Prize. We can hear two of them collide as ripples in space-time a billion light-years away. Our reach toward the black hole's exterior is one of the triumphs of the scientific age, and its interior is the one frontier that reach can never cross. We can compute it in extraordinary detail. The chaos of its Mixmaster churning, the ceiling of its curvature, the doubly exponential collapse of its volume, the two clocks that disagree by an eternity. But we can never send a probe in and receive its report, because the horizon that makes the black hole a black hole is precisely the surface that forbids the report from returning. It is the only object in nature we can characterize thoroughly and observe never. What does it mean to know so much about a place from which no knowledge can return? It means physics has reached a genuine edge. Not the edge of what we can calculate, but the edge of what we can confirm. And it is a mark of the maturity of the science that it can state exactly where that edge lies and refuse to pretend it lies anywhere else. The clock on your wall is still running. The next moment is still coming, and you still cannot turn to avoid it. That was the anchor we began with, and now you can see it was not a metaphor at all. It was the literal geometry. Inside a Schwarzschild black hole, the direction toward the center is time. Not like time, but time. The same unavoidable forward carry that delivers you into the next second, no matter which way you face. The singularity is not somewhere in front of an infalling astronaut. It is later. It is their next moment, arriving as surely as yours arrives for you. And no engine, no maneuver, no effort can steer away from it, because there is no away in the direction of the future. That is the deepest, widely true fact about black holes, and it is the one almost no one is told. Space, in there, becomes trajectory. Let me bring this exploration to a close. We began with a clock on a wall, and a next moment you could not avoid. And we denied the picture nearly everyone carries, the singularity as a pit at the dead center of the whole. In its place, we found something stranger and better supported. The signature flip inside the Schwarzschild geometry, where the metric coefficient changes sign at the horizon. The radial direction r becomes timelike, and r equals 0 becomes a moment in the future rather than a point in space. We watched the light cones tip over in the Kruskal and Sgr A map until every allowed path pointed inward, and we found that the maximum survival time from horizon to r equals 0 is tau max equals pi over 2 times rs over c, less than a heartbeat for a stellar hole, and that struggling only shortens it. We followed Roger Penrose through the Raychaud-Dury equation and the trapped surface to the 1965 theorem that paths end robustly in any realistic collapse, the work that won half the 2020 Nobel Prize, alongside Reinhard-Genzel and andrea-ghez, and that the Event Horizon Telescope's images of M87 star and Sagittarius A star and LIGO's detection of GW150914 confirmed for the exterior. We walked into the chaotic BKL and Mixmaster churning of the classical approach, with its Kasner epochs and its doubly exponential collapse. We crossed into loop quantum gravity and loop quantum cosmology, the discrete area gap, the bounce at 41% of the Planck density, the Ashtekar-Olmedo-Singh transition surface, the Planck stars of Ravelli and Vidotto, the black hole fireworks with their two wildly different clocks. And we followed the Kerr ring singularity, the genuine timelike exception, to the cosmic censorship that mass inflation and the de Fermo's look and look-O results appear to restore. Here is what the evidence shows. In a non-rotating black hole, the singularity is a moment, not a place. This is settled, uncontested geometry. And it is the answer to the question this began with. The classical singularity is almost certainly not the final word. The near-universal judgment of physicists is that quantum gravity intervenes before any true infinity is reached, because an infinity in the equations is the theory confessing its own limit, not describing a real feature of the world. But what actually replaces it? A bounce? A transition surface? A Planck star? Or something no one has yet written down is unknown. Something halts the collapse, or transforms it, or turns it around at the Planck ceiling. Decades of work by exceptional physicists have not identified with certainty what that something is. And the reason the answer stays out of reach is not a failure of imagination or of mathematics. It is that the one region holding the answer sits behind a horizon that permits nothing to return. That is where the evidence leaves us, and it is honest to leave it there, resolved on the geometry, open at the edge, and unwilling to fill the silence with a certainty no measurement can supply. If you have found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds who want the mathematics, not just the metaphor. So look once more at the clock on your wall, and at the next moment, already on its way to you, unavoidable and quiet. Somewhere out there, at the center of a collapsed star, an astronaut who crossed a horizon long ago is falling not toward a place, but toward their own next moment, exactly as you are falling toward yours. The only difference being that theirs has an end the equations can no longer describe, and yours, for now, keeps arriving.